Okay, welcome everybody to the second talk of Siva Prasad Das. We're going to have today a brief discussion of supersymmetry formalism. So thanks a lot, Siva, again, and welcome everybody. Go ahead, Siva, please.
So good morning, everyone. Also, I'm very thankful to Professor Brambilla and Professor Brito and all of you. I mean, all of you for giving me an opportunity for an online seminar for the second time. So today I would like to, in fact, I first apologize because what I feel that I'm still under preparation. So you will see that my slides, some of the slides are not very well prepared, and also at the end, few of the discussion, I didn't have much time for a revision, but I'm very sorry for that. But let me start. So today, today we'd like to, and also most of you are mathematician, and please, I really don't also understand many part of the group theory. So if I mean, I certainly stuck. So please help me explaining more. Yeah, please. Yeah, please. Okay. I'll be very happy that if you say something more deeper. So today is like a brief discussion on supersymmetry formalism. So this is the contents, like a supersymmetry transformation on component field. And then we'd like to discuss about the superspace and the superfield. And then just one slide for the summary. So, you know, in the last week, we have started the scalar potential, which is like a V, which is like a mh square plus lambda h4. So here the h is basically in the last 2 weeks is a 5. So that means it is like a same potential that we start. This is the Mexican hat potential. So this is, so that's the potential we started. So the question is that why we need for supersymmetry? So you see that I really didn't put also the diagram because the diagram is very clear, but let us say that because in the last class, in the last seminar, we discussed about that whenever I have a Higgs has a fermion-Yoko coupling, which is like a lambda f h f a bar, because this is the term that the Higgs basically gives the masses to the fermion. Yeah. So when the electroweak symmetry breaking breaks, the Higgs get the vacuum expectation value. And this Yoko term, which is a lambda f, and the vacuum expectation value of the Higgs, which is a V, that gives lambda f into V f bar f, which is a Dirac mass term for any fermion. So this basically the necessary to give the massive fermion, for example, top quark, bottom quark in our case. But you can make a loop correction because we know the mass term is basically the order of the scalar. But you can have a loop correction, which is like a higher level. Yeah, because you have a 2-point function, and in between the 2-point function, I have a 3-point function, and this 3-point function makes a loop inside. So it's like a bubble diagram in some other physics aspect, like, yeah. So if you do the final loop correction for the Higgs mass, you will get that the mass correction, which is the del mh square, which is like a lambda f square by 8f square into lambda square uv, which is some kind of an cutoff scale of the theory that where I assume that I have to have, because the momentum integration goes to the infinity. So that certainly gives the divergent integral. So I have to have a cutoff that my theory is valid up to some ultraviolet cutoff, which is I defined as an lambda UV as large as the Glatt scale or the Planck scale. Similarly, if you take the other interaction term in the Lagrangian, which is like a scalar loop correction. So if you do the calculation of the scalar loop, so you know the fermion loop and the scalar loop, they have a two different kind of a diagram to give the mass correction for the Higgs. Yeah. And if you do the similar integration for the scalar loop, because in the bubble diagram, I can translate as a fermion, I can also have a propagation along the scalar. And the scalar loop correction, which is very important, if you do the integration for the scalar loop, you will see that my scalar loop integration, which is connected with the lambda s by 16 pi square. So you see that lambda s, which is like a scalar coupling, and lambda s, which is like a fermion coupling. So think about this lambda s, which is basically this lambda here, which is like a scalar coupling. So you will see that I have a divergence term, which is called the lambda square u, like which is called, in generally, this is the quadratic diagram. So that means, so this quadratic type, so if you, so once you get the full correction for the Higgs mass scale from the scalar as well as the fermion, you see that I have a divergent, quadratically divergent term appears in my theory. So you can immediately guess that, suppose if by construction sum of the theory, which is if lambda s, which is equal to twice of lambda f, so if I set some theory where these couplings are connected, then I can see that the quadratic divergent from the scalar loop and the quadratic divergent from the fermion loop, they cancel. I still have a remaining, have a log divergent, but log divergent is not very log function. So log divergent is basically soft. Yeah. So I still have a soft, like a very mild correction from the ultraviolet scale. Yeah. So this basically the idea that lambda s is equal to 2 lambda f. So you have to have an architect of some theory where I made that criteria and then I remove the quadratically divergent. Now, in supersymmetry, so you will see that most of the slides are very much text yet, but I really didn't find little time for correction. But let me go. So in the supersymmetry, we introduce in the, I mean, not me. I mean, it's a Wes Jumino, Julius Wes, Ferreira, Faye, yeah. So they are the architect of the supersymmetry. So in the supersymmetry, what it does is that it basically, I have an Q and Q dagger, which is like a fermionic operator, which is also carry and spin angular momentum half, because this is a fermionic character. And this basically, if you act on the Q on a boson, that gives to a fermion. And if you operate on the Q on fermion, that gives me a boson. So it is like you are changing. So you are changing the spin by operating an Q on a state. So in the standard model, you will see that in the standard model we discussed in the last class that we have a chiral fermion. What is the chiral fermion? Chiral fermion is that if I have a left-handed and the right-handed transform differently under gauge group, then we call the standard model, these are called the chiral fermion. And this chiral fermion is basically responsible for the parity violation interaction term. And these theorems, for example, this parity violation interaction terms and the chiral fermion, this theorem implies that if you make an anti-commutation of the QQ dagger, which is like a Pu mu, and if you do the anti-commutation, and in fact, this is the basic part of the anti-commutating Lie algebra, I mean, is called the grading. I will also come back later. This is basically the connection with the fermionic operator in the fermion space and with the connection to the translation space. So here is that this is the connection from the Grassmann space to the Lorentz space. I will come back in the second slides. So if you do this Q and Q dagger, which is C, you have a Pu mu and QQ and Q dagger or Pu mu Q or Pu mu Q dagger, you see that this is my commutation. P mu Q and P mu Q dagger, these are the commutation. So this gives me 0. So I'll come back what is this P mu Q and Q dagger means for. So you will see that I'll just remove that part here. Okay. So okay. So you will see that sorry. Say Lorentz boost and rotation as a spin 1, which is basically P mu, while Q and Q dagger as a spin 1. So these single particle states of a supersymmetric theory fall into an irreducible representation of the supersymmetry algebra, and this is called a supermultiplet. I'll come back also this point again. So what is that supersymmetry? So you assume that I have some kind of a state which is like a omega, and I have another member which is called the omega prime members. Then omega prime is proportional to some combination of Q and Q dagger operators acting on omega. So it's again the same like a Q fermion and Q boson. So now I have some linear combination of the operator which is acting on the omega and omega prime. So this gives me up to a space-time translation or rotation, which is, and you will see that minus p square is basically the Casimiri, which is basically the m square of the Poincare algebra. So this commutes with the operator Q and Q dagger, and with all space-time rotation and the translator operator. So it follows immediately that particles inhabiting the same irreducible supermultiplet must have equal eigenvalue of minus p square. So what is the eigenvalue of the minus p square? minus p square is basically p mu. So that means this is the mass square. So that means that if I have a same representation of the same super multiplet of I have a fermion, I have a boson. So this gives me the minus p square commutes with q dagger. That gives me the super multiplet have the same mass for all the candidate or all the multiplet of the in a super multiplet. Yeah. So this means these are the mass degenerate. So now there is a Q and Q dagger. That is also another property of the fermionics spin half operator. Q dagger commute with the generator of the gauge transformation, because we'll come back that what is the gauge transformation. Gauge, we are working on the standard model and we are going to the supersymmetries. The gauge field is basically E1 electromagnetic, SU2L and SU33. So these Q and Q dagger, they commute with all the gauge operator of the gauge generator of the corresponding gauge group. That means that it doesn't change any quantum number of the same super multiplet, whatever the gauge quantum number of the corresponding gauge group those particle has. That means they have the same gauge quantum number. That is also very important. So that we must have an U1, SU2L and SU3 degrees of freedom. Now there is another operator which is called the -1/2s, which is called the bosonic operator. Yeah, because whatever you take, whether it is a fermion or the boson, so -2s basically leads to a bosonic operator. So this operator, when you acts on some state, which is some kind of an I state, so it gives the eigenvalue. For the boson, it is a 1, and for the fermion, it is a -1. So now you make a complete set and you operate on the -2n operator, and you have an expectation value of the p mu I, which basically gives me 0, because p mu is an always commute with everything. So if you do the expansion, you will see that I have a minus trace of -1/2s, and this gives me 0. So if this gives me 0, so the only possibility is that since p mu not equal to 0, because these are the 4 translation, so the only possibility is that I have a number of bosonic degrees and the number of fermionic degrees in a super multiplet that should be same. So this is the criteria that -1/2s p mu II with all the candidate of the super multiplet that should be 0. So this gives me that number of bosonic degrees of freedom and number of fermionic degrees of freedom in a super multiplet that should be same. So what is the simplest possibility of the irreducible representation of the super multiplet? The first simplest possibility that I have an one wild fermion, which is a spin half, and two real means one complex scalar. You can also 2 real degrees of freedom, you can manifest it in one complex scalar, which is the degrees of freedom is equal to 2. This called in the supersymmetry language that chiral supermultiplet or matter supermultiplet or scalar supermultiplet. So these are the minimal irreducible multiplet of an supersymmetry. Yeah. So what is the next simplest supermultiplet is the spin half gauginos and spin 1 gauge vectors. So that the gauge vector is basically the spin 1. For example, in the standard model, E1, SU2, SU3, W boson, gauge boson, gluon. Yeah, they are basically the spin 1 gauge quantum number, the spin 1 gauge boson. Yeah, and the Higgs is a scalar. So you have in mind in now think about that whenever I consider about the Higgs. So the Higgs should be in the chiral multiplet. So if I talked about the photon, W plus minus, Z boson, or the gluon, they should be in the next super multiplet, which is called the gauge or vector super multiplet. Yeah. So then to include gravity, which I am not also I don't know much, but if you include the gravity has a spin 2 graviton, which is also the gauge quantum number for the gravity, which is a spin 2, and the corresponding gauge quantum gaugino, which is a spin half, because you have to always keep in that nv is equal to nv. So if you include one scalar particle, you have to also include the corresponding spin half particle, which is a multiplet. So spin 3 2/2 gravity, they also had a degrees of freedom is equal to 2. So this simplest structure is sometimes called in the literature n is equal to 1 supersymmetry, because there is no extra quantum number, which is like a q carries and spin half index, but I don't have any internal quantum number of the q. So I am only going to the minimum requirement for the Grassmann operator, which is the q, which is called the n is equal to 1 supersymmetry. Yeah, and which this has an rich phenomenological context, because this directly embedded or this directly explain about the standard model. So as I also discussed about in the last week, that these are my spin zero, spin half particle content of the standard model, and these are the quark, these are the lepton, these are the Higgs. And I have an because I have a supersymmetrized, so I have a spin zero column and I have a spin half column. So you see that HU plus, HU0, HD0, HD minus, although I am writing probably there is an typos in the text, so it should be like a tilde. That means the corresponding partner of the scalar to the spin. Similarly, for example, I have an UR and DR. So these are the, because the scalar quark that was not in the standard model, but because of the supersymmetrized, I start with the spin half, which is the doublet of the lepton, but I get back to the corresponding scalar or the spin zero particle the other way. And as I said, that they are generating with the same gauge quantum number. So all the quantum number of these gauge groups, they are the same. So these, and similarly for the vector field, so these are the vectors. So the first one is the chiral or the matter supermultiplet, which is called the scalar supermultiplet. And this is the part of the particle content of the vector supermultiplet. So you start with a spin one, because in the standard model all are gauge one. So the corresponding spin half particle, and they have the same gauge quantum number of the corresponding gauge group. So you see that, as I said, that so if you take the correction of the scalar as well as the fermionic, I have a term which is like lambda s and lambda f whole square. So if I said that one, so the supersymmetry is basically that I quadratically divergent goes away, and I still have a log term which is basically called the soft supersymmetry breaking term. So you can break a supersymmetry. Today we will not discuss about the supersymmetry breaking, but so once you break the supersymmetry, so if you have a log term presence in your quadratical divergence of the scalar mass term, this is called the soft supersymmetry breaking term. So let us talk about these are the super, these are the kind of like an Yoko Lagrangian. So this capital Q is not like the Grassmann operator that I started with the spin half operator. So this Q stands for the quark doublet, because I know that SU2L, because the quark in the standard model, they follow the doublet, and this delta mu, the capital delta mu, which has a standard model gauge covariant derivative, you know, probably the normal derivative, and once you make an gauge transformation of an covariant of a derivative, so to make the whole theory as a gauge invariant, so you have to have some kind of a connection with the gauge field, and that gives the covariant derivative. And depending upon your gauge group, so you have an corresponding terms. For example, this is the term of the SU2, this is the term of the U1, and so that my whole theory, the Lagrangian, is a gauge invariant. And from the standard model, you get an W and Z boson mass because of this mixing. So this is basically the Yoko term of the standard model, and which is very important, and we'll see later. So let's start with the condition for the notation. So I start with the x wave, p means the four momentum. These are the covariant derivative, and these are the metric of my -1, 1, 1. So metric has a signature, and minus p squared is equal to minus m squared. This is called the on-shell condition. And these are the projection operator, and these are the Dirac equation for a fermion in a 4-component notation. Whenever I talked about the psi d, this is a 4-component notation. So gamma mu, gamma phi are the Dirac matrices, sigma mu, sigma 0. These are the Pauli matrices in the 2-component form. So here I'm not very expert, but I will tell you the main flavor of that. So there is a transformation which is an x prime mu, which is the lambda mu nu, which is a Lorentz generator, because these are the Lorentz transformation. So the Lorentz transformation forms a group such. This is called the orthogonal 1, 3 R. 1 and 3 is basically a non-compactness, because my signature of the -1, 1, 1. So that's why the non-compact form. This is called the generalized linear 4-dimensional real group formation, which lambda t eta lambda is equal to eta, which is coming from the top line. And there is a subset of the Lorentz group, which is called the L plus, wherever I have a determinant of lambda is equal to 1. This gives me the special part. And there is an orthogonus, which is defined as an up arrow. So the orthogonus means that the lambda 0, lambda is equal to 1. That means I'm only working in the forward time direction. So if you do this, all this group of the Lorentz group, you will see that there are 6 operators which are Hermitian, and they are basically the rotation and the boost of the corresponding generator, and they follow a closed algebra, not exactly close, because there is some kind of a grading is there, and this grading will help us for the Poincare and the super Poincare that we'll see in the next. So the important is that Ki Kj is gives me back the rotation, and I didn't really write the I and j index for the rotation and the Kj in here, but you understood that they also carry an indices for the I and epsilon ijk, which is an Levi-Civita for the 3 dimension. And this I really don't know about the homomorphic and so, but you will see, I'll tell you the one flavor that why it is connected. So you can connect that locally homomorphic Lie algebra of the SO1 3R. They are basically corresponds to SO4R, which is like a special orthogonal real dimension. And there is an SL2C. I really don't know much, but probably you people feel what is I mean. So SL2C, I will come back, which is like a Lorentz transformation. Lorentz group, you can also make an complexified. Whenever you make an complexified, so the dimension will be reduced, and this gives me the SL2C. And you will see that whenever I go for the SL2C, I start with the Lorentz generator, which is the rotation and the boost. So when I complexify, I make another linear combination. So here, yeah, so I have a complexified linear combination, and this when I complexify the generator with the linear combination, that is a non-Hermitian, and they follow the closed algebra. So that means I have an SS, so it gives me the element of the S, and if I have an TT, it gives me the element of the T. So that means even in the subspace, I have a group. So my group algebra is basically closed by the complexified. And this is called the SL2C. And this SL2C is, so this S and T is my new generator of the group. And this is basically the SU2C and SU2C. So I have a new generator within the Lorentz subgroup, which is called the SU2C, which is the generator of the S and T. And this has a corresponding quantum number, which is called the N and M. And N and M take the value of the Z component of the generator, and that is basically the fundamental, this basically manifests the representation of the super multiplier. For example, whenever I talk the 0, 0, that means the Z component of the projection of the N and M. So this gives me the scalar representation of my particle content. If it is a 0 half or half 0, that gives me the 2 spin half. Because you remember that I start with the chiral fermion. So either it is a left projection or it is a right projection. That is corresponding to the value of the N and M of the corresponding generator of the SL2C. So that's the connection. Probably you people understood that whenever I write lambda, which is the generator of the Lorentz group, and M is the matrix form. So this has a connection in the 4th dimension of the Lorentz matrix lambda M, which is like a half of trace sigma bar M sigma M dagger. So here the sigma and sigma bar, remember these are the Pauli spin matrices. This is 2 dimension. So I have a connection with the 4th dimension with the 2 dimension. With I really didn't write the indices for the sigma mu nu and mu nu, but here you understood, all of you, that here is a connection that SL2C has an direct product with SU2C and SU2C. So this is basically the main part. And then comes the Poincare group. Poincare group is the nothing. Poincare group is that I start with the Lorentz group, and then I make another translation, which is a small mu. So Lorentz group plus a translation. This is basically the Poincare group. Yeah. So under Poincare group also follow the similar algebra. Yeah. And then I didn't really go here, but there is some kind of an extension because if you do the only Poincare, you will see that I am basically get back to the anti-commutation. But you know, whenever I want to get back to the Lie algebra, I should have an commutation. So whenever I go from the anti-commutation to the commutation, I have to add an extra spin half fermionic operator. This is called the Grassmann, and I'll come back to that. So these are called the graded Lie algebra. I mean, I really don't know much, but I will tell you the feelings. So the graded Lie algebra is such that, so I start with an L0, which is a Poincare, L1, which is an QA, which is like a Grassmann operator that I discussed before, because that changes the fermionic and the bosonic. And then I have an L2, if it is a translation, which is like which basically corresponds to the mu, then you can make a group algebra like L0, L1 is L1, L1, L1 is equal to L0. So these are kind of my grading, because whether the algebra is closed or not. And if you write that I have a full group, which is like a Lorentz group, I have an spin half group like a fermionic operator, like a Grassmann operator, plus I have a translation. So this basically called the super Poincare. So whenever I talk with the Grassmann operator with the Poincare, this I call the super Poincare algebra. And you can check that if this xk and xj, so any operator from the corresponding gauge group, so they have an this kind of feature, and that basically we needed to have an graded Lie algebra in the super Poincare transformation. Because Poincare, so because why we need the Poincare? Because Poincare is basically relativistically invariant. So I want to make my theory of the supersymmetry that should be relativistically invariant. So let us go for the free chiral supermultiplier. So please let me know if you have, after the discussion, that if I said something wrong, or please add more understanding from you. So I start with the free chiral supermultiplier. So when I start any theory, so I start with a free theory, because it only has a kinetic term. Yeah. So this is called the free theory. So so you see, not even mass, only kinetic term, because photon massless. So photon can only propagate. So I start with a free theory. So then I know that I have a scalar and I have a fermion. So a scalar follows the Klein-Gordon equation, which is like a del mu phi del mu phi. This is like a p square of the scalar particle. And fermion follows the Dirac equation. But here I am writing the Dirac representation in the while fermion. So the sigma mu is the two component. So I didn't really write that you can compose the Dirac fermion in a while or the while basis, where it is a Pauli basis or while component, two component spinor. So these are the kinetic term. And I assume, well, I mean, not me. I mean, it's in Weiss and Julius Weiss and Bruno Jumino. So they basically did the supersymmetry transformation formalism. So this delta is nothing but the supersymmetry transformation. So if I make a supersymmetry transformation of a scalar field, I get a fermion. And you know, the scalar has a mass dimension 1 and the fermion has a mass dimension 3. So the mass dimension should be matched on the transformation. So I introduced a parameter which is an infinitesimal, which is called the epsilon. These are the parameter are infinitesimal, anti-commutating, two component while object, and has a mass dimension -half to get correct with the corresponding mass dimension. Similarly for the depth, and for a global SUSY, for the global transformation, for whenever we talked about the local, in gauge transformation, there are two kinds. One is called the local, one is called the global. Local, it depends on the space-time coordinate. If it is a global, it doesn't change on the space-time coordinate. So whenever I talked about the global supersymmetry transformation, so that means this is equal to 0. And so far, I am only, we discussed today only on the global supersymmetry transformation, because global supersymmetry transformation doesn't really care about the, I mean, doesn't really think about the mass very carefully, mass of the particle. And mostly it is the free theory. Yeah. So global SUSY, and you can have a transformation of the whole Lagrangian. And similarly for the I transform for the scalar field, and I am assuming, I mean, Weiss and Berger, Weiss and Bruno Jumino, so they basically guessed, it was a guessing that what could be the possible harmonic transformation such that I have an Lagrangian which should be the supersymmetry invariant. So their idea was that I know the gauge invariant very well by now, and now I would like to supersymmetrize the theory. I change the scalar field. Now I have to change the fermionic field such that my whole Lagrangian is SUSY invariant, other than a total divergent term, because total divergent term is really not very important, because whenever you do the action, so the total divergent term gives me the surface term, and surface term goes away for an OLVF function. So similarly, so these are the, so that's the total derivative term. So that means my total action is 0. So this is the first requirement, my action is supersymmetry invariant. Yeah. And then this is also another important for any Lie algebra, that supersymmetry algebra that should be also closed. That means if you have two supersymmetry transformation, which is like a delta xi2 and delta xi1, and you make a commutation for any scalar field, you get back to a kinetic term of the corresponding scalar field. That is basically the connection that you will see, that whenever I have a QQ dagger, I have a P mu. P mu is nothing but the delta mu. Yeah. So you see that the commutation of the QQ bar or QQ dagger, which is the Grassmann operator, that basically manifested the part of that my SUSY algebra is basically closed. Yeah. So this is very, very important, the algebra close. Yeah. Probably you people know. And similarly for the fermion field. So in the fermion field, if you do the supersymmetry algebra close for the fermionic field, you will see that I have an kinetic term for the fermion, which is like a del mu psi alpha, and inside I have some factor. But the important point is that I have an extra piece. So this extra piece is a problem. Yeah, this extra piece is a problem. Then, but I know the Dirac equation. The Dirac equation for the massless Dirac field, psi bar gamma mu psi is equal to 0. And if you make a corresponding massless Dirac equation in the two-component form, this gives me the massless Weil form, and this gives the on-shell condition for the two-component Weil fermion, which is like a sigma bar mu del mu psi. And if you get that, so you get back to the extra piece from your fermionic supersymmetry transformation to get that my supersymmetry algebra is closed. Yeah, but there is no problem for the on-shell case. In the on-shell case, the supersymmetry algebra is always closed. So the problem is that whenever I go to the off-shell case, off-shell cases means that I have some kind of an extra degrees of freedom, which is basically coming from the mass term of the corresponding fermion. And you know that whenever I have a mass term, generally I have a longitudinal polarization. Yeah. So to get back to the longitudinal polarization of the gauge vector, so I have they introduced. I mean, not only Weiss and Bagger, there are many people like, I forgot their name. So they have to have an off-shell formalism, because they have to get rid of the extra degrees of freedom for the off-shell case. So for the off-shell case, they introduce one parameter, which is called the F, which is an auxiliary field. This called the auxiliary field. This doesn't have any kinetic term, only F dagger F star Fs. Yeah, and then you have a corresponding supersymmetry transformation for the F term, which is like a del mu psi and del mu psi dagger. And if you make an auxiliary for the supersymmetry transformation, you get some term which is like a del mu psi F star sigma mu F. And if you do the corresponding fermion term, because I have an fermion has a connection with the fermion has a connection with the auxiliary field, so I have a corresponding term. Now you make the supersymmetry algebra inclusion of the auxiliary Lagrangian, which is F star F, into the whole Lagrangian, and then you see that my supersymmetry algebra is closed. So I'm really, so the idea is to have the off-shell is that I want my supersymmetry algebra to be closed, and I get help from an auxiliary field. Auxiliary field doesn't have any kinetic term. So if it is a kinetic term, it has another problem. So, and then my scalar fermion and auxiliary as a whole is supersymmetry invariant. And here, this is one of the issue that I discussed about, that these are the degrees of freedom. So whenever you include the off-shell mode of the theory, so I have a large number of degrees of freedom, and you will see that the degrees of freedom for the fermion is basically 4. So you get to the 2 degrees of freedom for the F is equal to 2 to get to the extra degrees of freedom for the auxiliary field, to get what I said about the NB is equal to NF criteria for the operator of -1/2s into p square II, that should be equal to 0. So I'm matching to the degrees of freedom also as well. Yeah. So then I have an interaction. So these are my free Lagrangian for then scalar, fermion, and auxiliary needed for the closeness of the algebra. And now I add to the interaction, because you see that if you go to the dimension analysis, you can see that this has the new interaction term has a mass dimension is equal to 4, because this is the 4th dimension. Because by the way, I'm also I didn't mention that, but we are working on the 4th dimensional n is equal to 1 SUSY. There are many hard dimensions, but I don't know that this for the string theory people. So we know that the mass dimension of the Lagrangian density, these are the Lagrangian density, that should be less than or equal to 4. Yeah. So then I allow that I have an L interaction. These are the free field. The up is the equation 29 is the free Lagrangian. But I know that the free Lagrangian basically doesn't gives me anything very interesting, because they don't couple each other. So I need to have an interaction term. And then I allowed an interaction. I mean, not me. I mean, they allowed because their idea was that I have to match this supersymmetry with the standard model. So they allow some interaction term, and the interaction, they also gauge that what could be the form of the interaction term. That should be minus half wij psi j, because you have an understanding that psi j, this is the mass term of the fermion, and then wifi, because I want to generate the mass in a supersymmetry way, and wifi, this is the connection with the wi function with the auxiliary field, and then I have an fi, then charge conjugation, and then L is interaction is equal to, these are the kinetic term and minus potential energy, which is called the U. And these wij, wi, xij, u, these are the polynomial of the scalar field or the complex field with the mass dimension correspondingly, because each has an mass dimension maximum I can allow up to 4. So the first term is a 1 because psi has an already have a mass dimension 3. So I can only a maximum allow wij is equal to 1 and the corresponding for the other. So this L interaction minus wij psi j plus fi. Yeah. So there are some kind of I forgot the condition that why I'm removing the u and fi star. I forgot that criteria. Probably you cannot have an I forget that. I forget that why I come back from here to here, because there are some criteria that xij and the u, they should be 0. I forgot that, but I will tell you one day. Okay. So that means there are some criteria that should be. Let me check. Just is a 1 minute. So these are the criteria that I can remove the corresponding term. So I left back with L interaction, which is like a wij, psi j, and wifi and cc. And to get the so you know the L interaction doesn't have any indices for the ij, but psi j, I didn't discuss about the while component field for transformation form. So this psi j also have an indices which is on Grassmann indices. They are connected. So psi j is equal to psi j psi I. You can check that. From the while algebra, psi j is equal to psi j psi I. That means this is an ij symmetric. So this gives me this Fiat transformation of the fermionic. That also tells me that wij is equal to also symmetric for the ij indices. And then now we change the transformation of the Lagrangian of the supersymmetry transformation of the Lagrangian by pieces. And now what is the four spinor supersymmetry transformation of the Lagrangian? Yeah. So then if you do so, this is really not very straightforward, but if you do so, you will see that I got something like a epsilon. Epsilon is not a parameter. Epsilon is a supersymmetry transformation parameter, which is a mass dimension minus half. Yeah. So if you do so, you will get then you have to also get the Fiat identity for the corresponding fermion. It's like some similar kind of an Bianchi identity for the generator. So it is a cancel if and only if. So you have to exploit this Fiat identity in the L interaction. So this will cancel if and only if delta wij by del phi k is totally symmetric ijk. So that means I have to exploit the Fiat identity on the supersymmetric transformation for the L interaction of the four spinor part, and this will cancel if and only if my these are like a derivative of the wij and del psi k. This is total antisymmetric of the ijk, and no terms for the there is also no term for the epsilon plus psi plus ik psi I psi j, and that gives me that wij, which is I started with wij is a function of a psi and psi star, which is a complex scalar field. Now this condition gives me that wij is holomorphic in complex phi. That means it is only contained, I mean holomorphicity I also know, if people know much better. So that means some complex analytical form. So wij can only form the real phi degrees of freedom or the real phi, and one can have an idea that what could be the form of the wij. So this is also a case that if I have an wij which is called the mij, this is some kind of a mass matrix for the fermion that I will come back in the next slide even here. And if I have a form yijk, this y is is an Yokowo coupling. This has an have in mind that this I have an Yokowo coupling Yijk phi k, and fermion Mij is an symmetric matrix and Yijk is an Yokowo coupling. So you can have an Wij from an generator of the delta square delta phi I phi j of the W, and this W you can guess that what could be the W, this W, to get back to this Wij, and this W could be that form. This is called the half of Mij phi I phi j plus 1 over 6 Yijk phi I phi j phi k, and this is called the superpotential. So you see that how I got the how the people got the idea of the superpotential, because the idea of the superpotential is coming from the interaction of the supersymmetric transformation of the L interaction in the force spinor, and using the idea of the holomorphicity of the Wij function. So this is basically called the superpotential, and you see that this is only contain the mass matrices for the fermion, and this Yijk is the Yokowo coupling for the fermion. We'll come back. So that. So then what is the interaction for this delta Ij? So you write back to the interaction term of the, this is not the force spinor, this is only the derivative interaction now. So whenever I called about the derivative interaction, that means this has a connection with the scalar momentum with the fermion. That means I have a fermion and scalar is propagating. Yeah, this is like a, you can think about that. I have a scalar particle is propagating and fermion is at rest, and it is a connection term. So this is also, I have to have a whole supersymmetry. So this is I have a supersymmetry, and it can be checked that this Wij del mu phi j I can write in a total derivative form. This total derivative form I can only write if Wi is equal to Mij phi j and half of Yijk phi j phi k. So this is, as I said, this is the first indices. So the W is basically the superpotential. Now I have to go back to the what is the Wi. So you can see the Wi by this criteria, the supersymmetry transformation of the kinetic term of the interaction, kinetic term of the scalar, that gives me the first index of the first derivative of the superpotential, and that gives me the Wi, and Wi is also that form from this derivative. You can always add a linear term, which is in the last week I discussed about the linear term, which is like called the tadpole term. So this linear term you can always add, and the Li should have a mass dimension 2, because the superpotential has a maximum mass dimension 3. Yeah, superpotential has a mass dimension 3. Yeah. So then you can, so this is my full superpotential. Yeah. So the linear term doesn't really make any sense because it doesn't have any other effect. Yeah. So then the Lagrangian free plus interaction part. Now you have an Fi star, which is the auxiliary field, and Wi-Fi, which is an auxiliary field with the first derivative of the superpotential and the corresponding term. Now you got to the equation of motion for the fermionic, the auxiliary field, and you get that equation. Fi is equal to minus W star and Fi star is equal to minus Wi. So that means since the addition of the auxiliary field to get rid of the supersymmetry algebra is closed, and I don't have any kinetic term, and this superpotential formulation, after having the superpotential, I got the corresponding equation of motion, and the equation motion, this is an on-shell equation of motion, and this on-shell equation of motion is basically fixed, that auxiliary field is nothing but the Wi, or auxiliary field square is nothing but the minus Wi. Yeah, Wi is a function of the phi I. Just now I discussed the Wi I can generate from the scalar potential. So Fi is now a function of scalar particle. Yeah. So then you get back to the corresponding, the whole Lagrangian to replace the Fi wherever you Fi, you get back to the kinetic term of the scalar kinetic term for the fermion, and then I have a scalar. This is the fermionic mass term. This is the fermionic mass term, and this is my Wi. W star is the Fi star. So this is my whole Lagrangian after fixing the whole term. So then this is called the scalar potential of my chiral field or the matter field. We are so far, we are only discuss about the chiral field or the matter field. That means only the scalar particle and the fermion particle and their interaction. So once you put the V5 star, so WK star and F star K FK, you will see that this is my the whole potential of my chiral supermultiplet, only chiral supermultiplet. Yeah, so this is my scalar potential of my chiral supermultiplet. So I have a mass term, I have a trilinear term, I have a quartic coupling term, and the full Lagrangian density you can have it, and you can have a corresponding equation of motion for the, because I have a mass term. So if you have an equation of motion, you get the corresponding mass term because I already have an interaction term. Yeah, so this gives me the corresponding equation of motion for the mass term. I think you can similarly do for the gauge supermultiplet, which is the next representation from the gauge supermultiplet, because we need the gauge particle to be part of the supersymmetry. Similarly, A mu is a gauge particle, for example, photon, and A is the corresponding like an generator indices for the corresponding gauge group. So this is the normal gauge transformation, just like an U1 electromagnetic, and this is the corresponding structure factor of the corresponding gauge group. For example, SU3, these are the color factor. And correspondingly, these are the gauge field, which is like a spin 1, and this lambda is a gaugino field. That means this is the corresponding super partner, but spin half. Yeah, this is called the gaugino field, and they also transform same gauge transformation as the gauge particle. This A is the adjoint representation of the gauge group, for example, U1, SU2, SU3, like 1, 3, 8. And if you put F is equal to 0, which is the structure factor, which is 0, and for any non-abelian gauge field, you can get to the abelian gauge. Similarly, so this is the convention for the normal electromagnetism, that mu is the 4 vectors, the Riemann potential and the vector field, vector potential. These are the electric field, these are the magnetic field, and these are the corresponding degrees of freedom, because the degrees of freedom is also should match also for the gauge supermultiplet. So for the gauge supermultiplet for the off shell, exactly similar like an auxiliary field for the scalar multiplet. So I have to have a gauge algebra closed, and it doesn't close, so I have to introduce another auxiliary field which doesn't have any kinetic term. This is called the D field. So D is equivalent to the auxiliary field for the chiral supermultiplet, but it is here for the gauge supermultiplet. And again, for the degrees of freedom should be matched. And then you start with a gauge Lagrangian, which is like F nu nu, which is the corresponding electromagnetic gauge field. Yeah, and if you add an AA, these are the corresponding, for example, the gluon field or high dimensional field. And this is the gaugino kinetic covariant term, and half of DA is the F star for the supermultiplet. These are the Young-Mills field strength, which is like the normal electromagnetic field strength plus the coupling with the field with field. So you see that this structure factor is basically coupling with the gauge particle itself. Yeah. So then covariant gaugino, this is the lambda is the covariant gaugino. This is the corresponding gaugino covariant term. Yeah, with the corresponding gauge quantum number for the same. So now you do all the supersymmetry transformation for all the fields available in your theory. And to get the supersymmetry algebra closed, because this X stands for all the component of the field that should be closed, and you will see that for that I need and this is basically the now the supersymmetric gauge interaction. Yeah, gauge interaction, because it was before, it was only the free part. It was only the free gauge field. Now I have to introduce the gauge interaction, and whenever I have a gauge interaction like a psi I going to psi I plus ij lambda a, this lambda is the generator, and Ta is the corresponding parameter of the gauge group with the corresponding xi. And if you do the corresponding covariant transformation of the phi field, this is that form. And if you do such that, this you can check that. I mean, this I really have not much did it recently, but you can check that the supersymmetric gauge interaction with mass dimension less is equal to 4, you can only allow from your free Lagrangian plus gauge interaction, you can only allow 1, 2, 3, this 3 way. You can only allow that only the 3 gauge supersymmetric gauge interaction that you can allow. Yeah. So then now you add to this corresponding gauge interaction in your Lagrangian, and then you make a supersymmetry variation again, and then you got the full chiral, which was we discussed before, and then the gauge, and these are the corresponding 3 terms that you get from the corresponding the maximal possible 3 gaugino gauge particle interaction terms with the chiral field. So that means, so the second line of the equation 49 is important. So I have an L chiral, I have an L gauge. So the third term, the second line gives me these are the only possible interaction that I can allow supersymmetrically with the chiral field and the supersymmetry field. Yeah. So this above equation 49 is SUSY invariant. This is also the one of the most important criteria of all this, that this equation 49 that should be supersymmetry invariant. So here the supersymmetry invariant means that you allow the whole Lagrangian supersymmetry transformation with all the component field. This is only happen if the Wi and the Ta phi I. Ta is the, remember, the Ta is the corresponding generator of the, or the corresponding gauge parameter of the corresponding gauge generator, and Wi is the I got it from the first derivative of the phi I from the scalar potential, and phi is the scalar field. So this is only happen if this condition is met. Yeah, this is a very, very important very important criteria. So this condition is met, then you get the corresponding equation of degrees of equation motion for the supersymmetric gauge invariant, and you replace, you got similarly for the Fi I got minus Wi. Here you got the corresponding equation of motion for the d term of the gauge field. You got dA, which is minus G phi star Ta phi. So you remember that Ta is the corresponding parameter. Ta is a parameter. Lambda A is the generator of the gauge group. So again, the dA, which is the I reduced, got the equation of motion for the D field for the gauge criteria, and I found that the D is also function of the phi alone. Yeah. So D is a function of phi alone. So that means the complete scalar potential, which is nothing but the Fi star Fi plus dA star dA. So this is called the whole scalar potential of my chiral plus gauge plus interaction. So that means I am having a whole potential of the scalar potential from the F term and from the D term. So these are the main result of so far. And remember that whenever in the last seminar we discussed about the scalar potential for the Higgs field, you will see that there is an H squared GAH. So this is basically the second term of the corresponding. So here you see that I have a GA star. That means I have an lambda square H4. So the lambda square, which is the quadratic coupling. So this is basically fixed by the gauge coupling of the equation of the criteria of the 50 and 51. So that was the connection that my scalar quadratic coupling is basically not free in the supersymmetry formalism. These are fixed by the criteria of the 50 and the 51. So these are the scalar potential of the chiral gauge and the chiral gauge interaction. So that is basically the complete scalar potential of my SUSY theory. So Prof, I think I mean it will take another 15 or 20 minutes for the superspace and the superfield. So the first formalism that I so far discussed about, these are the basic formalism of the supersymmetry transformation formalism by the Weiss, Jumino, Ferreira formalism. But superspace and the superfield, these are the formalism developed by initially, I mean mostly Abdus Salam and his student J. Strategy from New Zealand. So Prof, if you allow me, I can go for another 15 minutes.
Yes, it's okay. It's okay. 15 minutes. No problem.
Okay. So these are the superspace and the superfield. So you know, I start here. You see that I start with the same number of degrees of freedom, 4 bosonic and 4 fermionic. That was this is a different aspect, by the way. So this is a different formalism, but at the end it gives the same result. So you see that we start Abdus Salam and J. Strategy. They start with the 4 bosonic degrees of freedom and 4 fermionic freedom. So x mu, which is an 4 vector in our normal space time, which is a 4 degrees of freedom. And theta alpha, alpha runs from 1 to alpha dot also 1 2. So 1 2 3 4. So it is an the degrees of freedom match. So initially I start with the match degrees of freedom. Then what is done is that superfield is a function of superspace coordinate. So this basically define my coordinate in the superspace. So superspace is nothing but the ordinary force space plus theta alpha, theta dot, theta dagger alpha dot. So this, the whole things as in superspace. Supermultiplet component, superfield is a function of superspace coordinate. Supermultiplet components are united into a single superfield. So whenever we discuss about the component formalism in the last section, so here you will see that all the components you can enfold it, you can tagged in an one superfield. There is the most important aspect of the superspace formalism. Any infinitesimal translation in the superspace is basically global supersymmetry transformation. Remember the global supersymmetry transformation that was in the past, in the discussion before, it was the condition that del mu alpha is equal, del mu epsilon is equal to 0. So that was the global supersymmetry transformation. So this, if I translate infinitesimally in the superspace, that is exactly equal to the global supersymmetry transformation. Yeah, that is the connection. And then since this theta alpha is an fermionic coordinate, it is an Grassmann operator. So the Grassmann has a follow like it is a different algebra like a normal. And the Grassmann, because it is an anti-commutative, so I can go up to maximum 2 power. Here I assume that I have such kind of a Grassmann, it can go up to only 1 power. It is just for an understanding. Yeah. But the normal Grassmann here, because this is a wild component, that should go for the 2 component. So here you will see that the most important of the Grassmann algebra, one of the math lecture I was really saw also the Grassmann people talked about. One of the beautiful about the Grassmann algebra is that in the Grassmann space, the differentiation is same as the integration. Yeah. So if you check that, the differentiation is same as the integration. And the Dirac delta function of the Grassmann space, if I have a direct delta function of the Dirac space integration of the Grassmann space, it is nothing but the translation. So this is the criteria of the equation 60. And then as I said, as Salam and Strateday formulated, basically Strateday, his student. So they formulate a superfield which is like a coordinate of the x theta bar, and all the component field they basically put in together, and this is called the superfield. So these are the corresponding Frege form kind of and Frege identity or the Weil algebra of the Grassmann space. I am not really going to all details, but these are not difficult. So these are the algebra of the Grassmann. But the algebra of the Grassmann is that, as I said, that the integration is same as the differentiation. So if you integrate out del square theta sx x bar, so you get projected out. You get a projection that I only project out the B field and the Xi dagger field and the D field. So this small d is so corresponding. You'll see that there is an also one-to-one correspondence. D is D. You will see that this D is basically the capital D of the gauge field auxiliary field. Yeah. So then you projected out delta square theta dagger sxx. So you get C theta small d. Yeah. Then you get the integration of the del square theta dagger. You get only the D. So that means, so because so whenever the idea is that we have to form some kind of a Lagrangian density from the superfield. So once I got to, that means to get the Lagrangian density from the superfield, you have to get rid of the extra 4 degrees of freedom from the fermionic, because those are the theta alpha, theta dagger alpha dot, theta dagger alpha dot. So we get out after having the last line of this one, and then this will give you to the Lagrangian density, and then you get the action after doing the integration of the d4x. So this is exactly like a similar. So since the delta theta alpha, so these are not a kind of an, you can think about, I really didn't revise myself very more clearly, but you can think about this is some kind of an covariant derivative in the Grassmann space. So I am forming some kind of an Q alpha. It is not only the delta delta theta alpha in the ordinary sense of the del mu, but I have to add some kind of an Pauli spin matrices with the delta mu. So these are the connection that I have a wild connection, which is an spin basis, and I have a connection with the normal four-dimensional translation. So these are kind of the connection with the corresponding Q alpha, and they follow the linear algebra. And again, similarly, the -1s, that was the corresponding in the supersymmetry transformation -1/2s. So these are the Grassmann odd and even. And then this delta, then you come to the supersymmetry transformation. In the supersymmetry transformation of the superfield in the superspace is nothing but you act on the operator. So what does it mean? What is the meaning of this Q alpha? So Q alpha hat is not, it is an operator in the superspace. And this operator, because these operators with the corresponding parameter with the epsilon, which is the Grassmann minus up, they will act on the superspace function. Superfield is nothing but the superspace, the function in a superspace. So I am acting on an operator on a function, and then you get the corresponding superfield, and you got the Taylor expansion on the supersymmetry parameter, and I have a translation in the, so a supersymmetry transformation can be viewed as a translation in the superspace in the following way. So I change the theta alpha going to epsilon alpha, I change the theta alpha dot going to epsilon alpha dot, and I am changing the x mu. I am x mu to x mu plus the connection with the Grassmann and the Pauli. Yeah. So this similar transformation takes place for all components of the superfield, although I'm not mentioning explicitly, but the idea is here. The idea is the main. Yeah. So the idea is that. And now, since this is an operator, the Q alpha hat is an operator. Yeah, it is the Grassmann operator. It is a spin half operator. So now you can make can I check that how the operator algebra follows? And you can see that if you do the algebra for the anti-commutation of the Q alpha Q by beta dot, you will see that they exactly get back to the graded algebra form. Yeah, so you see that we started with in the supersymmetry transformation. I started with Q alpha Q beta dagger is equal to sigma mu p mu. So I got back the same way. Yeah. So that basically mimics the same structure for the supersymmetry transformation. Here it is called the chiral covariant derivative. So these are the chiral covariant derivative so this is a very important point is that, so this is very important point. The derivative of a superfield with respect to theta alpha, theta bar alpha dot are not superfield. This is a very important criteria. Suppose I start with the superfield, which is a function in the superspace. I make one derivative with the theta alpha. This is not a superfield because this is not holding the supersymmetry invariant. So you see that the top line, which is the equation 69, it has an intrinsic characteristic that this tells me whether it is a supersymmetry invariant or not. Yeah. So then, because it is not supersymmetry invariant, because the term in the bracket is not a superfield. Yeah. If it is a superfield, it is not. So then similarly for the gauge covariant derivative formalism, in the superspace, you make an chiral covariant derivative, which is called the capital D alpha and D bar alpha dot. And you will see that equation 71, which is like a chiral covariant derivative. It is a gauge invariant in the superspace. Yeah. So this the D alpha is necessary to make the superfield has an gauge in supersymmetry invariant in the superspace. Yeah. So then this is the form. Again, you can check all these algebra and you can check that they also have the required algebra is needed have an consistency. Yeah. So then you can check that equation 76. Equation 76 is basically the Lagrangian density. It will give you to the Lagrangian density, and the equation 77 tells me that I have an consistent cutoff. That means I cannot really go up to the like a theta. Yeah, this is like a Taylor cutoff because of the Grassmann properties of the algebra. So equation 77 gives me that my cutoff, my expansion cutoff. So again, now I think I'll finish in 5 minutes. 5 minutes, I'm done. So then this also need to be a little bit more for myself, but so chiral superfield is an superfield, so this follows that criteria. That means if I have an phi is an superfield, so if I have an chiral covariant derivative del bar alpha dot, which is equal to 0, so this is the condition that gives me the chiral covariant derivative, the chiral field. The definition of an chiral field in the superspace is the equation 78. So if any superfield equation follow that equation, this is an chiral superfield. Yeah. So then you can take the corresponding coordinate. I can have a translation in the coordinate in a different. I change from the x mu to theta dagger to y mu to have an chiral covariant derivative in a very simple form that I will show. That you can work on the x mu basis. You can also work on the y mu basis in the superspace. Yeah. So the usefulness of the y mu basis is that the definition in the something characteristics, which is very simpler, or once you project out, you will get the project out directly. Yeah. So then you got the corresponding chiral superfield in the, you see that this is, that's why it is much simpler from equation 83. Equation 83 is a very simple form in the y coordinate. So this is called my chiral superfield. Similarly, I got the corresponding chiral derivative, and you got the corresponding the whole superfield expansion in terms of the component. Remember the equation after equation 86, the capital phi in the left hand side is the superfield. So this superfield has all the components, small phi x. This small phi x is the real scalar field, or I mean, normally it is a complex scalar field, because in the next slide I have a phi star. So this phi x is the real scalar field that I started with in the supersymmetry transformation. For example, this phi x is the fermion. This fx is the corresponding f term in the chiral field. So then chiral superfield supersymmetry transformation, you have to do also all the component supersymmetry transformation, and such that once you do the supersymmetry transformation, all this, you will see that my phi, I can get the chiral superfield from a generic superfield, which is the last equation, equation number 90. That means if I know the chiral covariant derivative, and if I know the generic superfield in the superspace, I can construct the chiral superfield just by d bar s. I get the double projection of the chiral covariant derivative on the superfield, and I get back to the chiral superfield. What is the vector superfield? Vector superfield, as I said, that vector field or the gauge boson field is in the adjoint representation of the gauge groove. The eigenvalues are real. These are the adjoint, probably people know more, a real representation. So this means that I should have a vector field that should be a real. So the real criteria is imposed by the equation number 91. That means that should be V is equal to V star. And if you put so, and the corresponding condition of the component field gives me that equation, and this I can write as a generic, most generic, the vector superfield in the superspace. And similarly, you have to have a component transformation of the superfield, and you get that you get the corresponding transformation on the superfield component on the superspace. A very important point is that this is very important point, that a superfield cannot be chiral and the vector at the same time. So that means either a superfield is chiral or vector. They cannot be together at the same time. But if you given a chiral superfield, you can construct a vector superfield. For example, since I know vector superfield is a real, so given a chiral superfield phi, you can construct phi plus phi dagger, phi star, or I phi minus phi star, or phi star. These are the vector superfield, because this is needed. Whenever I do a gauge transformation of the vector field, you will see that I phi minus phi star is needed for a gauge transformation on the vector field on the superspace. This is called the supersymmetric gauge invariant in the superspace. Yeah, that is needed for that. So yeah, that's why I come up here. So this is called the super gauge transformation. But here, for a simplicity, we are only discussing about the U1, but the corresponding SU2, SU3 is also there. So these are called the super gauge transformation. That means I have a vector field. It can go to V plus I omega star minus omega. This omega and omega star, these are the chiral superfield. But chiral superfield gauge transformation. Yeah. So because this is a gauge transformation. So chiral superfield gauge transformation parameter. So if you do so, yeah, and there is you have to have a component match, and you can understood that This called the supersymmetric gauge. This called the supersymmetric gauge or the super gauge transformation. This basically, this is the most important result. So once you make a super gauge transformation on the vector superfield, you get rid of all the auxiliary fields from the theory. This is called the Weiss-Jumino gauge. So this V, which is called the vector superfield in the Weiss-Jumino gauge, Julius Weiss and Bruno Jumino. So this is the one of the most important construction. So that means I don't have any, I am completely eliminating the auxiliary fields from the vector superfield. So I think now only the construction of the superspace Lagrangian. I really don't have. Also, I have to have a recap more stuff, but I think this is not difficult now. So you get projected out the d term, or like the Lagrangian density. The first integration gives me the Lagrangian density in the fourth space, and then you integrate out the Grassmann space, and then you got the Lagrangian density, and this A is the action. And Vd is the d term of the vector potential. Psi f is the f term of the. Oh yeah. So you know, as I said, if you see the properties of the del square theta dagger, you will see that this will only projected out theta dagger term, which is called the small d. So that means it is only projected out the capital D term. It is only projected out the capital F term, and you get that. And these are the phi d, which is like a 1/4 del mu phi, but it doesn't have any problem because this is as a whole derivative of del mu, and it will integrate out once you take the action. So the equation number 100, it doesn't really affect because the phi is a well-defined function. So similarly, I really have to recap more about that, but I think you got the idea. So if you do the double projection of the, you get a -4, and you got the corresponding d term of the vector potential, which is -1/4 d bar v. So that means how I got the Vd, I get a double chiral projection operator on the vector superfield and take the f term, and that gives me the Vt term. Yeah, these are beautiful, in fact. So finally, the Lagrangian, the superspace, you get the chiral superfield, you got the d term, you got the f term, you get it projected out, you got all the product between them with the corresponding transformation of the spin, and you got the corresponding Lagrangian, which is the phi star I, phi id, and w fi and f. This is the first part, which is the scalar potential for the holomorphic function of the phi, and these are the d term. So this gives me my whole Lagrangian of the d term and the f term of the superspace. And if you take the corresponding interaction, and you got the equation number 106. So the first term, which I didn't mention that, which is like a phi star I e 2g q I v into phi I. So this is the term where my chiral field and the vector superfield have an integration, has a connection, has an interaction. And if you make a Taylor expansion, the exponentially, you get 1 plus x square plus x cube plus x4. Those are the tree-level term, first order term, second order term, third order term. So this first term is basically taken care all possible interaction, tree level, first loop, 1 loop, 2 loop, 3 loop. So these are the these are my whole Lagrangian of my supersymmetry, chiral, vector, and chiral plus vector interaction. Yeah, and I think I'm okay with that. And I think these are the references that I followed when I was like a student. Julius Weiss, Jumino, Salam Stratede, Pierre Faest, Sergio Ferreira. These are very, for the mathematical people, equation number 4, I recently found Gates and Cecil. Beautiful, beautiful. And there's a lecture, and 6 and 7, Professor Manuel Diss and Professor Harvey Diner, that they both have the supersymmetry review. And I'm very happy that I worked both with both of them. I worked both with them. And for today's lecture, what I discussed today, I totally follow the one of the famous supersymmetry premier, which is also, he's also co-author with Harvey Diner. I totally follow the reference number 8, line by line, text by text. So one can start with that, and it's beautiful. But if I have little more time, I could do it more. But it's a summary. So supersymmetry transformation, we discussed Weiss and Jumino. And superspace formalism, salam strategy. We didn't time for the supersymmetry breaking today, but maybe some other time. With this. Thank you so much for all of your attention.
Thanks a lot, Siva. It was very good.
Thank you so much, Prof.
If there's any question, comment, you can do it by chat, or you can take the microphone, please.
Please. Hello.
Yes, we're waiting. If somebody want to ask something.
Hello.
Yes, we're
Any
waiting.
questions? Please, for the mathematics people, please tell me about group theory or something. Please. I really don't know, but those are very interesting. For example, SL2C and SU2C connection, which is the corresponding. Those are. I really didn't find time more for preparation, but if I would have little more time, I would prepare more on that aspect. From the one of the references that I missed for the Poincaré and the first two slides of the Lorentz transformation, and then the Poincaré transformation, super Poincaré transformation, graded Lie algebra part. This is one of the reference, very famous people, Muller Kirsten. So they also have an review on the supersymmetry. Very good review, very early days supersymmetry construction review. It's a beautiful. So I tried to recap yesterday, but yeah. So thank you so much to all of you.
No, thank you. Thanks a lot, Siva.
Thank you so much.
Thank you.